So hello and welcome everyone. I hope you've all been having a wonderful morning and we can start off the afternoon in a good fashion. So let's just get right into it. So our device is, or our project is lead contamination separation in water via microfluidic lab on chip. So just to give you a brief outline of what we're going to go through, first we're going to identify the problem and give you a little bit of background about it. Then we're going to go towards the design outline and verification, how we got to the design and how we verified the design prior to building it. Then on to fabrication, where we'll talk about the fabrication principles of how we got the device to where it is. Then we'll talk a bit about the testing protocol and the results, and then we'll go on to some future work just to see where our device will be going. So first we'll talk about the problem description. So lead in drinking water poses a significant health risk in even developed countries today. While you can see what we've seen at Flint, Michigan there, which is terrible, terrible water pollution. And in 2013, it was estimated that lead pollution accounted for 850,000 deaths worldwide, represents about 10% of the burden for intellectual disability, as well as a large portion of stroke and ischemic heart disease. And the majority of this burden is held by medium and low-income countries. And the WHO has additionally identified it as one of the 10 chemicals that pose a serious public health hazard. And there's no known safe blood concentration of lead. So any amount of lead that makes it to your blood can lead to intellectual dysfunction as well as serious health risk. And so because so much of this is undertaken by medium and low income countries, not everybody has access to all of the equipment they need. Right now there are two extremes for lead testing. It's either you have lead test strips, which are a qualitative measure. You can't get an accurate concentration. It's not always easy to tell the difference between the colors. They're inexpensive and they're fairly inaccurate in terms of the accuracy of the test. And then on the other end, you have laboratory methods such as ICP, inductively coupled plasma spectrometry, and atomic absorption spectroscopy. And these are very specialized pieces of equipment that aren't available everywhere. Even in Canada, it's not always easy to find these pieces of equipment, let alone in countries that are affected by this. In a third world country like the Congo, for example, you would have to fly your lead samples to somewhere in Europe to actually find accurate testing. And it's just very expensive. So with this in mind, this is where we'll talk about our design. So we wanted to make a device that can be coupled with existing laboratory procedures in order to get accurate lead testing while using less expensive and less selective equipment. So if we can make some sort of pre-concentration device that allows us to prepare lead samples ahead of time and concentrate it, we can use less sensitive equipment like UV vis, for example, which is widely available almost everywhere. Then we no longer need this specialized equipment, so we can lower the cost to the end user as long as our device is also inexpensive. And as long as we have a modular design, it means that we can implement it into any existing lab technology. Okay, but why microfluidics? So we decided to use microfluidics for a couple of reasons. The primary one being that we can ensure pure laminar flow, which makes electrophoretic separation more effective for separating positive, neutral, and negatively charged species. As well, it means that we can stick to this small form factor, which allows us to maintain a modular design that can be implemented in all sorts of things. Additionally, if we keep it small, we can continue to use this electrophoretic separation because it's not scalable or efficient when you get to higher scales. So this is our solution outline. It's a two-stage solution, which is a separator stage made of an electroplated silver electrode that used a template-based growth. And then we have a concentration stage, which relies on an anion exchange membrane that acts as a semi-permeable wall of charge for electrophoretic concentration of lead in water. So we did a bit of design verification beforehand by doing simulations in multiphysics software. The first of which being the separator, which demonstrated the efficiency of separation of our lead in water at a 9-volt DC bias, which is accurate for what our device is looking for, because we want something that can be eventually something that could be handheld and powered by something like a 9-volt battery. Then we did a concentrator stage simulation as well, where we simulated the effectiveness of the membrane given the parameters from the manufacturer, and it was showed to effectively separate lead and water in solution. So now onto the fabrication. So we'll talk a little bit about the materials we used, and there were many engineering trade-offs that we went through when we did this. I'll try and keep it short just because this is a limited time that we have. Basically, there's PMMA, silicon glass, and PDMS that are all used interchangeably in industry. And we stuck with the PMMA strictly because it keeps the cost low, which is one of the main goals of our device. It's a reasonably hydrophilic substrate, so you can use a water-based solution. The problem is that it's difficult to seal when compared to other solutions like oxygen plasma treated PDMS. And again, it's easy to process because it's a little bit softer than all of the other applications. So we were just able to mill it.
The next fabrication trade-off we're interested in talking about is kind of the scale of the device as a whole. Generally, when we're working with microfluidics, you can operate at one of two scales. You can be at the hundreds of micron scales, or you can be the ones and tens of micron scales for the channel size. So we went with the hundreds of micron scales, and this decision was also made in tandem with the selection of the substrate material. Since we were going to be using PMMA and milling was our best option, you can't really mill channels that are only a few microns wide, or if you can, that equipment has not been made available to us. So the reason why we wanted to use these channels is, as I mentioned, it's easy to mill. This is an inexpensive method of fabrication. Because your channels are much larger, you're going to be reducing the capillary forces that would require a larger pressure to drive your flow through the device. Defects are more correctable by hand, so if you have rough edges from your milling machine, you can just take some sandpaper. It's very easy to identify these rough edges either with your finger or just by visual inspection. You can sand them down. The membrane that we're going to be using for the concentrator stage can also be effectively placed in the device by hand. We don't have to use any fancy equipment to correctly locate it in its position. And the electrode fabrication is actually one of the major trade-offs, because when you go to this large, we need to create essentially a 300 micron thick layer of silver. And to do this, it actually requires a lot of time. In fact, it took us about 10 hours per side to make these electrodes, which was long, arduous, and a bit expensive. So now we're going to go into a bit of a detailed presentation of exactly the steps we took to mill the device. So very quickly, we created some CAD files and we imported them into the software of the milling device that we used. It was an Autolab milling machine. We milled the PMMA slides and we removed some of the rough edges using sandpaper by hand as needed. We then began to fabricate the silver electrodes, which I'll mention in the next slide, and we then milled the remaining microfluidic channels. So to make the silver electrodes, we started by creating a sputter shield so that we could effectively control where on our chip we are going to be having silver growth. And then we just simply used some silver sputter and we sputtered directly onto our slides. It took about 10 minutes on 1-minute cycles, and it was conducted in argon plasma. We next did some electroplating, and just in a silver silas solution. We assembled the setup, something similar to what you see on the right. That's actually a picture from our presentation. And we electroplated as to keep the voltage below negative 0.9 volts. This was selected because if you go much higher, you start to get some defects appearing in your electroplating. So your silver becomes non-homogeneous. You also start to hydrolyze water, which is going to create an oxygen-rich environment, which will then proceed to corrode away your electrodes, and you have to start all over again. And we continued to electroplate our electrodes just by visual inspection until we could see that the channels were completely filled for them to be filled. And if they were ever raised at all above the channels, we just used some nitric acid and a cotton swab, and by hand we were able to selectively and gently etch away any excess silver that we didn't need. Next, for the final assembly of the device, we fabricated a lid, again with the milling machine, and we milled essentially a negative of the channels. And that was done because it helped kind of with the sealing process as a whole. We used a plastic cement to seal around the channels after having placed the membrane in position. I'll just give you a quick explanation. So over here is actually where the membrane was placed, and you can see the two metal contacts going in towards the center condensing band. We used, again, plastic cement in a combination with silicone caulking to seal all around the edges of the device. And we attached a pump adapter through the same manner, and we also soldered some wires onto our silver contacts so that we could apply the 9-volt bias. Next, we're going to talk a little bit about the testing we performed. So the testing protocol was relatively straightforward and simple. We made a stock solution of lead acetate. This is a highly soluble salt that is easily accessible and not too expensive. And so we just made that in 18.2 mega ohm centimeter millicu water. And we made solutions of 30, 50, and 100 milligrams per liter of lead. That was corrected for the lead concentration because we were no longer interested in the acetate as of this point. We ran the samples through the device at approximately 0.4 milliliters per minute and at 9 volts, as we mentioned. This flow rate was selected as it was one of the parameters we had used when doing simulations earlier on in our planning. Next is that we did, we diluted both the output and input solutions that we made and received by an equal amount. I'll talk a little bit about why in a second. And then we delivered all of the samples to ALS for them to process and determine our concentrations of lead, and they used an inductively coupled plasma methods. We went with ALS because they were fast, not too expensive. We were able to afford it. And then they are highly reliable. They just used an EPA protocol, an industry standard, to find out exactly what our lead concentration was. If you could go back one slide, please. As to why we used these concentrations specifically and as to why we diluted them, our original plan for determining how much lead was in the water was actually to use an ion chromatography method, which used a cation exchange resin column as well as a conductive meter to find out what the concentration was. However, we ran into a couple of problems in that when we immediately applied our lead acetate to this column, it was actually filled with a bicarbonate, and lead bicarbonate is highly, highly insoluble in water, and it instantaneously precipitated out. But furthermore, their auto sampler needed about 10 milliliters to run, and we didn't want to necessarily run our device for that long because it would not only take a long time, but the pumps that we were using to drive flow through our device only could hold 2 milliliters before needing to be refilled. So it would have slowed the whole thing down immensely. So let's talk about the results we obtained, because these are perhaps the most exciting thing. So these are the results we obtained from ALS. I'll very briefly explain this slide to you. We have the device outlet concentration using the right-hand y-axis in red, and the input concentration is on the x-axis, and the concentration ratio is on the left-hand axis in blue. So what these results show is that the output concentration was consistently and actually verifiably higher than the input concentration. The concentrator effectiveness actually decreased as we went to higher and higher concentrations. And the reason why we think this took place is because when you get to higher and higher concentrations, there's going to be a solvative force or an osmotic pressure that's going to counteract the ability of the membrane to effectively separate water from the lead. So to explain that very briefly, because we have a high concentration gradient on one side, water is not going to be readily available to pass through the membrane in as great amounts. Next slide, please. So let's give a brief summary of what we accomplished and what we obtained. So the device was successfully designed, it was successfully fabricated, and successfully tested. Our results indicated that we received an average of 30% increase in concentration across the 3 different concentrations that we tested. Finally, let's talk a little bit about our future works and where we could go from here with our project. So the first thing we'd probably be interested in doing is actually construct a second prototype. We'd be interested in looking at the use of potential multiple concentrator stages. This was so that we could obtain a higher concentration ratio, right? We got a 30% increase. We'd like to see 10 or 100 times if possible, and even see if that's an option. We'd be interested in using a different substrate, for example, glass. And when we reduce the contact angle with having a very, very, very hydrophilic surface, this will actually help counteract some of the solvative forces that prevent water from flowing across the membrane in the first place. Because in effect, you'll get the channels also pulling liquid through the membrane. We'd be interested in different channel methods. Glass is a lot more difficult to mill. And we'd also be interested in different sealing methods because you can't use plastic cement. We also are very much interested in exploring other potential applications for our project, and I'll talk a little briefly about them right now. So one of the advantages of using our separation mechanisms as we did is it relies almost entirely on electrostatic principles. So this device is not limited just to lead. It could be also used for mercury, nickel, copper, or any other heavy metals. In addition to, it could also be used to separate anions and neutrally charged species just in the separator phase. If you wanted to concentrate negatively charged species, we'd swap out the anion exchange membrane for a cation exchange membrane, and the device should function just as well. Lastly, we'd be also interested in potentially putting a sensor on our chip as well. So this is just a separator and concentrator phase that makes it easier to detect lead. Why not put a sensor right on the chip as well? The reason why we didn't originally set out to doing this in our design project is because it was recommended against doing so by our supervisor, Dr. Carolyn Wren. One idea we had for the sensor is actually using some technology that Dr. Wren herself had fabricated, and she uses two concentric metal rings. The outside metal ring is conducted to a frequency generator, which then excites the inner metal ring. And when you have solution passing over the inner metal ring, a capacitive gap within this ring will change its resonance frequency, and you can use that when connected to a frequency counter to kind of see what your comparative capacitance change is and what the resulting solution concentration is. It acts not too differently in principle from a quartz crystal microbalance. Anyways, that is the end of our presentation. What questions do you have?
So any questions? Start if people want a second. Go ahead if you're ready.
Okay, so I guess a question in terms of the design goals. So do you have any idea like what concentration you would need to concentrate your
Yeah, exactly.
suitable for your
Yeah. So in terms of what you are to expect in like a modern sort of water system, obviously it's different depending on where you're sampling water from, but you're looking at around an 100-fold increase that would be necessary. So between using something like ICP versus where the detection limits of UV vis or fluorescent spectroscopy are. So it's about 100-fold.
So where does your solution now fall on that scale?
So it's definitely low, but we're optimistic for a couple of reasons. The first of which being that because we can show that it consistently increases the concentration, it's just a matter of optimizing the design either by increasing the volume to volume ratio, so because that's what the principle is based on, is volume of drain channel versus concentrated channel. Additionally, because the device is so inexpensive to manufacture, like cents on the dollar, under $1 per device, you can run many of them in tandem to achieve a greater concentration effect. So, well, one device is low, because the cost per device is low, then the implementation of multiple modular pieces together can achieve that goal.
Yeah, I have a very similar question. Do you know the range of detection for the test strips?
For the test strips, so it depends on the test strip and the brand. Like, it depends on the different mechanisms. In terms of sensitivity, it's anywhere between like 30 parts per billion, I believe, and 100 parts per billion. But it depends on the strip, and the main issue is that
How does that convert to your concentration unit? You will use a milligram per liter, right?
right, but because ours is using a volume to volume ratio, like we only selected that concentration range because of the original detection mechanism that we were going to use, which was ion chromatography. It still concentrates in the same manner, regardless of the concentration inside of the device, because it works based on electrofluidic principles as well as a volume-to-volume concentrating mechanism.
Just want to have the order of magnitude, like the concentrations you tested. If you convert to ppm, ppb, what is it?
We were in the ppm range, not
Yeah.
the ppb range.
Yeah, and that was strictly because of
That was what was recommended to us from the We were in the ppm range, not the ppb range, because that was strictly what was recommended to us by the operator of the ion chromatography conductance meter.
Yeah.
We used an outside source for that, and she said you need to be in this range for us to reliably detect things.
Just curious, the design verification you showed, you don't have a slide number, by the way.
Oh, sorry.
What did you use for the verification earlier? There are two plots.
Oh, yeah.
You generated.
These are COMSOL simulations, so it's multi-physics simulation software, and it's
What is showing on here?
this is the concentration of lead ions in solution. This is in the ppb range. Yeah. So these are the figure on the left is the concentration of positive lead ions which are moving into the positive charge channel. So this is across the capacitive gap. And then the concentrator stage is the same thing, but it's showing the interface between the two channels is where the membrane is. And it's showing the theoretical efficiency of the membrane at those concentrations.
Okay, so we should stop there so we don't get out of synchronization. Thank you very much.
Thank you.
Thanks.